So, today we are going to discuss spinning by adhesive and felting process. So far we have seen that the spinning is done by either putting twist or by wrapping. Now, we will learn that there are other ways to hold the fibers together, so that the fibers as a bundle in the yarn form can really sustain some load, that is, they are strong enough to take some load, or they should have some strength. Now, the very mechanism of strength development in a yarn is traditionally by twisting process. We know that by twisting we force the fibers to follow a helical path, and while doing so fibers also keeps on migrating from core to the surface of the yarn and surface to core part of the yarn, and they follow it in a very periodic manner, and as a result the yarn as a whole can really be strong, because the fibers will not slip. The helical configuration will allow the development of radial forces or transverse forces between the fibers, and as a result the fibers will grip each other, and hence they will not be able to slip easily. So, that is one mechanism which is traditionally followed, and we do it on ring spinning. Exactly, this is what is done, or on compact spinning also the technique is basically same. Now, when it comes to wrap spinning, here the bundle of fibers which are in the core, they are actually wrapped, and there are two different ways of wrapping that we have already learned. One is you wrap it by the same fibers, same constituent fibers, and the other is that you wrap it by an external filament. And this wrapping process, whether it is done by the same fibers or by the filament, is actually going to again create some transverse force when the structure as a whole is extended, and therefore, the frictional resistance developed between the fibers against slippage, and hence the bundle of fibers which are there in the core, they can resist slippage, and therefore, they are strong enough to take some load. So, these two techniques are very popular, and there are so many machines or so many technologies which work on the principle of forcing the fibers to follow helical path or trying to wrap the core part of the yarn by either same fibers or by the external filament. Now, there could be another technique by which we can have some strength in the yarn. Ultimately, any staple yarn is basically an array of discrete fibers. So, because it is an array of discrete fibers, as I am drawing it here, and it is a parallel array. Since the fibers are parallel, obviously, if I try to pull them, the fibers will simply slip. So, we have to somehow create a bond between the fibers, and that bond is a mechanical bond which we create in the form of twisting or wrapping, and that is a bond basically is a frictional bond. Now, there could be another way or some other techniques to create these bonds. So, if we use some kind of glue in between the fibers and the glue holds the fiber together, then also the entire the array of fibers will be able to sustain some load. So, that is what we are going to learn. The other one is the felting. Felting, I think many of you have already learned this particular word, the felting, and the fiber which is most prone to felting is wool fiber. And what is the reason for felting? The felting is because the wool fibers have scales. If we see the surface of wool fibers, which you might have studied in your textile fibers course, you will see that the surface of the wool fibers are not smooth, there are a lot of scales on them, and these scales can interlock when the fibers are in the form of a bunch, and there could be some process in which we can make the fibers to interlock, and this interlocking is because of the presence of scales on the surface of the wool fibers. So, we will see that how felting takes place, and we are actually many of you maybe already know that felting is very common when we try to wash a woolen sweater in the washing machine. The dimensions of the sweater, which is made of 100% wool, they generally shrink, and this shrinking is because of felting between the fibers. So, through this felting process also there is a possibility of folding the fibers together. That is only possible because of scales which are there. So, now we are going to discuss the various technologies which have been developed. Now, first thing that we will take is bonding. So, bonding methods could be with the help of binding agent or with the help of adhesive fibers or with the help of some polymers. So, bonding methods could be either by some binding agent or by some adhesive fibers or by some polymeric materials. Now, the processes which have been developed, they are known as Pavena or Tuilo-New process, where binding agents are used to produce a yarn. When we use adhesive fibers, the technique is also known as Tuilo. Different companies have developed these techniques, and when polymers are used, it is known as Bobtex. So, processes are known as Tuilo process or Bobtex process. Now, we are going to discuss these processes one after the other. First of all, the principle of Tuilo process. The principle is that since we have to have some kind of binding agent or adhesives, so mix certain water soluble glue or adhesive fibers with the main components. We have to have some way to mix a glue which is water soluble and some other adhesive fibers which also could be water soluble. then the glue and the adhesive will hold the fibers together in the yarn state. That is the purpose of the glue, that they will be able to hold the fibers which are there in the cross section of the yarn together. And once the yarns are converted into a woven fabric, the interlacements will be able to hold the fibers together, and therefore, once these yarns are converted into fabrics, we do not need the glue, because the interlacements which are there, they are good enough to hold the fibers together. So, when we make the fabric using these yarns which has some kind of glue or adhesives, we can now remove all these glues and adhesives. And if we remove them, the glue and the adhesives is no more there, and what we have left is a fabric where all the fibers are free from glue and free from twist, but they are held in positions by the interlacements. Every interlacement point is a source of pressure point, and depending upon the frequency of interlacement, we can see that a fiber may be held at 20 or 25 or 30 different points, depending upon what is the ends per inch and what is the peaks per inch. At so many points, if a fibers are held by some pressure, obviously the fabric as a whole will be stable enough. That is how we know this sort of processes have been developed, because we know if the glue remains, then the yarns will be very, very stiff. So, we have to get rid of the glue once the fabric is made, and therefore, you will have a fabric made of 100% fibers, no glue, and the fabric will have the right handle, so that they can be used for different purposes. The only thing negative about these processes are that the process is costly, because removal of the glue and adhesive makes the process costly and therefore, economically less attractive. That is the only thing. So, therefore, we have to think of that which kind of products, for which kind of products we can use this kind of technology, because the process will be costly. Therefore, the yarn that we will make will be costly, the fabric that we will produce will be costly also, and the cost is coming because the additional process that we need to get rid of the glue or the adhesives. Now, an outline of the process is shown here on the right hand side, and what we see here is that there is a source of sliver, and this sliver has 5 to 11% of PVA, polyvinyl alcohol. It is a kind of adhesive fibers, and they are available in filament form, and they are also available in the form of staple fibers. So, these fibers we have to mix with either cotton. If we want a cotton yarn, we can mix with synthetics, maybe polyester, or we can mix with viscose rayon, or we can mix with a combination of polyester viscose blend or polyester cotton blend. So, proportion of adhesive fibers could be between 5 to 11% or 10%. and they can be mixed on a draw frame, because we know in the draw frame we can easily maintain the blend percentage very well. Then we have to give 2 to 3 passages, it is draw frame passages, to the sliver, so that the fibers get well dispersed within the sliver and the sliver becomes quite uniform as well. So, therefore, 2-3 passages are basically very good. Dispersion of the adhesive fibers will be better and the sliver also will be quite uniform, the fibers will be straight and parallel. So, that is the idea. Now, these drawn slivers becomes my feed material to the system. So, this is the sliver can and we feed the drawn sliver which is containing that now 5 to 10% of PVA fibers. So, they first pass through a drafting zone 1, as it is written here, is drafting zone 1 consisting of 2 pair of rollers, and we give attenuation which could be to the order of 5 to 10. So, some draft we give it maybe 5, 6, 7, 8, 9, that is the range is between 5 to 10. Some attenuation happens to the sliver. So, sliver becomes 5 times or 10 times thinner. Then that is called pre-drafting zone or pre-draft. So, we have given this much amount of draft, but this much amount of draft obviously is not sufficient to make a yarn. From sliver to yarn, the total requirement of draft to be to the order of 200, 300 in this range, depending upon what is the count of yarn you want to produce. Now, after drafting, what we do? We make the fibers to pass through a false twister, which is shown here, and this is a water jet false twister. To twist this strand, because we want to give it a round shape. So, if you the very quick way to transform a flat sheet of fibers into a round shape is by the method of twisting. So, if we give some twist and we use a false twister here, because we finally do not need any twist at this stage. So, false twister 1 will be twisting the bundle of fibers which is moving out from the draft zone 1. At the same time, because it is a water jet false twister, it will wet the fibers. So, fibers will be in wet state, because we need to have some water in order to make the PVA fibers. We have to see PVA fibers are there. So, PVA fibers are soluble in water. So, if they get some water, the PVA fibers become quite tacky and they will be able to hold the fibers together now. And once it moves out of the false twister, it go to the right hand side of the false twister, there will be no twist left there. So, twist will be present on the behind the false twister, but there will no twist present in front of the false twister, because we know that false twisting basically means that the S and J twist they cancel each other, which I have told in many times, and therefore, in front of the false twister there is no twist left. It is again a basically bundle of fibers with PVA fibers dispersed within them, and the PVA fibers have already solved a bit and they have become tacky. Now comes the second drafting zone. In the second drafting zone, the draft can go up to 40. So, there is a range in which we can keep the draft here, because now after the second drafting zone we have to reach to the stage of the yarn or dimension of the yarn. So, we can keep a draft of 30 or 35, 32, whatever we require. Accordingly, we can keep the draft and we bring the bundle of fibers to the dimensions of the yarn, whatever yarn count we want to produce. After this, we see another first twister number 2. This first twister, what is the speciality in it? This second first twister is basically a steam jet first twister. Steam is there, basically means there is a heating. So, this will again make the drafted products quite round, and this will warm up to a temperature of 70 degrees centigrade. So, that complete dissolution of PVA fibers actually occur, or at 70 degrees centigrade it may not occur, probably depending upon what is the what is the temperature which it may not occur, but most of the fibers will dissolve and maybe complete dissolution may not have occurred at this stage. So, complete dissolution can only take place when it goes from here to the dram dryer here. Here we keep it the temperature to the level of 140 degrees centigrade, and when the yarn is passing through it, it can warm up to a temperature of 80 degrees centigrade, and at that temperature dissolution will be almost complete. So, here partial dissolution occurs when it is passing through the first twister 2. The temperature can go to the extent of 70 degrees centigrade. After that it goes to the dryer, where the temperature of the dryer is 140 degrees centigrade, but depending upon the whatever residence time is there, the temperature of this yarn can go up to 80 degrees centigrade. So, that all the PVA fibers are completely dissolved, and after that the dryer is already there, the drying will also occur. So, simultaneously the drying also is going to happen, and once the drying is over, we are going to form a package. So, by the time it is coming here, it is a dried yarn. So, at this stage it is a dried yarn containing PVA fibers which have already dissolved and now they have dried. So, all this that adhesive which is in dry state now is holding the fibers together. Because it is first twister, so there will be no twist in the fibers. So, fibers are held together by the PVA, and this dried yarn is now going for package formations. So, the package is here. So, that is how the actual machine is going to work. We have 2 drafting zones and 2 false twisters. One false twister only using normal water, the other false twister is using steam. Next, we see what kind of raw material we can use. So, some data is giving here. As I said, we can have either synthetic fibers or cotton or that blends, or whatever viscose rayon we can use lyocell fiber also, synthetics we can use polyester, we can use acrylic, whatever fibers we require we can use it. The linear density of the fibers could be anywhere between 1.4 to 6 decitex. Staple length could be 30 to 80 mm. Generally that means fiber should be long, and the length of the adhesive fiber, that is PVA, is typically 40 mm and its linear density is close to 1.7 decitex. Finer the fibers, we need more adhesive fibers. Now, the yarn that we make, how it will look like? This yarn you have to remember that at this yarn stage they are still having lot of glue within them. The cross section will be little flat, though you expect to be perfectly round, but actually it is not round, because when you try to wind the yarn also, there is some amount of pressure which will be there, and that will make the shape of the yarn cross section little flat or more oval type of shape. Elongation will be low, stiffness will be high. Why? Because there is no twist in the fibers. Since twist is not there, the initial modulus is going to be quite high, and because the same reason the elongation also going to be quite low. So, all these yarns will show higher stiffness and low elongations. In comparison to the yarn made from the same fibers on other technologies, that is either on ring spinning or maybe on vortex spinning, evenness is similar to ring yarn. Process characteristics, what is important is high energy consumption, because you have to have steam for the first twister that works with steam, and we need a dryer also. So, overall the power consumption is high. We have to use water also. We do not need any water while spinning yarn or ring spinning technology or rotor spinning technology or jet spinning or vortex spinning. There is no need of any water, but here there is a requirement of water. And other thing is, important thing is, adhesive or binder must be washed out completely. If it remains, the fabric will be stiff. So, washing out only happens after the fabric has been made. Machine specification that we have is spinning position is 8, whatever commercial machine is available. Delivery speed is very high, 500 to 600 meters per minute. We have not seen the other technologies having similar this kind of speed. Even vortex spinning also having a speed at the most 500. That is what the machine manufacturers claim. Commercially, it may run at 350 meters per minute or maybe 400 meters per minute. Delivery speed here is quite high. Count that can be spun varies from 6 NE to 40 NE, or that is 100 ticks to 15 ticks on the finer side. And it can be used in the bath towel, interlining, coating material. Some typical use are shown. So, bath towel we can use it, that is we get rid of all the fibers, all the binding agents, and only fibers are left. So, we can in the toweling fabrics they can be used, and in the case of interlining also this can be used, and for coating material, that if a fabric needs further coating and all, then this fabric can be used there also. Then we coat it. by some other material. So, that is all about binding by some adhesive agent. Here the PVA fibers act as a adhesive agent or as a binder. After this, the next technology that is comes to our mind is bonding by polymer. The process for this particular technique is known as Bobtex process, which was, we will come to that, where it was developed. And within this there are two categories or two types. One is integrated composite spinning known as ICS, and the other is aerodynamic brake spinning, short form is ABS. So, these are the two different processes which are there. First, we will discuss about Bobtex process. In the Bobtex process, which was developed in Canada, we extrude polymer through a spinneret with a filament yarn in the core. So, there has to be an extruder, and there has to be a method by which we can feed a filament in that particular extruder. Then release separated staple fibers on them. And twist them together. So, this is the main principle, you can say. Basically, you are extruding a polymer along with a filament in core, then release some separated fibers, staple fibers, whichever you want on the surface of that polymer. So, in the core you have filament, on the filament surface there is a layer of polymer, and now this on the surface of the polymer we will have staple fibers. So, we have to have a means to introduce staple fibers, and then this whole filament, polymer, staple fibers, they are twisted together and we get a round shaped yarn. This is what is known as Bobtex yarn. Now, if we want to show the sketch of the process, a schematic is given here. What you see here, first of all, that extruder is what we required. So, we have extruder and the molten polymer is introduced into this extruder. This is my molten polymer. So, it goes inside the extruder, and on the extruder there is a filament which also go inside the extruder. So, we have to have a mechanism by which we can feed the filament. So, polymer is fed in a molten state, actually they are fed into the extruder, and at the same time I am also feeding a filament. The polymer is extruded through the spinneret and then it is drawn, see it is going down towards a laminating rollers. So, what we have here is a filament in core, and that filament is also surrounded by a polymer matrix, and the filament could be either monofilament or it could be also multifilament. So, the filament is coated with polymer, because both of them are passing through the pinarets. So, the filament remains in the center and it is surrounded by the polymer matrix. We say the filament is completely coated by the polymer. After that, what we have to do is we have to now introduce staple fibers, so that staple fibers gets an opportunity to get stuck to the polymer matrix. For that, what we have, that we have two sliver cans, one on the right hand side and the other one on the left hand side. From both the cans, the sliver is introduced. The sliver is moving towards this opening unit, this central opening unit, it is going there. And here we have basically an opening roller, two opening rollers will be working for two feed sliver, and the fibers will be opened out or separated from each other by these opening rollers, and these separated fibers will be landing on the laminating roller, which is shown at the center, and the fibers will be picked up by the polymer. That is what is going to happen here. So, we will have a situation where core contains the filament, we have a polymer matrix, and polymer matrix picks up lot of staple fibers. We get a composite yarn because three types of material is there: filament, polymer and staple fibers. All of them are twisted together by a false twister. Here is that false twister, this false twister is here, false twister is going to twist them together. The false twister will introduce some twist in the yarn, because some true twist, you see, though false twister we mean that false twister should not leave any twist in the final yarn, because we feel, as we have discussed earlier about the false twisting principle, that because the twist directions are different in the upstream and downstream side, therefore, when the upstream part of the yarn flows to the downstream part, the twist in the upstream part and the downstream part, they cancel each other, and therefore, no twist is left in the downstream part, while the upstream part always shows the presence of twist. So, if the twister is here, this part will may show some false twist, but the part below will not show any false twist. That is what the false twister is going to do, but some true twist is left in the yarn, because why? Because one end of a fiber, while one end of the fiber is twisted, the other end can rotate and release the opposite torque. That is the reason. When the other end cannot release the torque, that means in that case the torque present in the front part of the fiber and the back part of the fiber. This back part and front part is in reference to the false twisting position, false twisting units position. So, when the part in front of the false twister and the part in behind the false twister, if both of them have exactly same amount of torque, in that case whenever the part behind the false twister moves downstream, they lose all the twist, because the torque will cancel each other, because they have different senses. But if the tail part of the fibers is allowed to rotate or they have some freedom of rotation, then twist present in the trailing part will be little less than the twist present in the downstream part, and hence though most of the twist will be cancelled, some twist will be still left, and that is why some true twist is seen in the fibers after the false twister. This is possible because, as I written it here, that the fibers within the polymer matrix which is a plastic state, hence they are free to rotate. So, there is the trailing end of the fiber bundle which is getting false twisted. This fiber bundle, the trailing part is within the polymer matrix which is in a molten state, and therefore, the fiber ends have some freedom to rotate because the torque is present there, and hence some true twist will be seen in the final yarn. So, typically the final yarn constituents are polymer can vary to the percentage, let us say 20 to 50%, filament percentage could be 10 to 60%. So, remember filament is going to give it the strength to the entire yarn, and the filament, if it is strong, the yarn is going to be strong. Staple fibers can vary between 30 to 60%. So, these are the ranges in which the polymer filament staple fibers can be varied, and we will be able to produce a yarn which is a yarn having a filament, polymer and staple fibers. So, staple fibers will be seen on the surface. Specifications: spinning position 2, the machines which is available. Delivery speed can go up to 600 meters per minute. Raw material could be filament, polymer, fiber. Fiber could be polyester, cotton or some other fiber, whatever we want. Fiber length is to the order of 64 mm, long fibers. Count could be 2 Ne to 20 Ne, that is 300 ticks to 30 ticks. These are the typical yarn count that can be spun. Feedstock should be card sliver. So, that is our starting point. We take card sliver and then we carry on the process. Advantages are the process is fairly simple and can be applied to any fiber and polymer. The production rate is quite high, ranging between 4 to 10 times the production of a ring frame, but it can go up to 600 meters per minute, whereas the ring frame production rate could be 15 meters per minute. So, very high, and even it could be much more than 10 times, more than 10 times it could be. Elimination of some of the processes such as drawing, roving and even winding, that is the advantages, that we get rid of certain processes. The yarn structure is shown here. Typically, you have filaments, then this is the polymer, and you have staple fibers. So, this is the typically to structure the to look like this. The yarn consists of core of mono or multifilament 10 to 16%, 60%, but usually it is 30 to 40%. A polymer which could be polyamide, polyolefin or intermediate layer 20 to 50%, and staple fibers which could be between 30 to 60%. It is a continuous filament strand with staple fibers attached to the surface. The surface will show the presence of staple fibers. So, that a typical spun look probably will be visible. The addition of the staple fibers to the polymer restricts their freedom, increasing yarn stiffness. Stiffness is going to be high, because the filament inside is also straight and parallel. They are not following helical path, and the polymer is also there. So, the entire structure is going to be stiffer. The yarn is regular, bulky, but relatively weak and extensible. The weakness and extensibility is due to the undrawn polymer. So, whatever strength we get because of the presence of the filament. So, that is all about this particular yarn. That is called, the process is known as Bobtex, where we have filament, polymers, staple fibers, all of them are present, and we can produce some yarns as the diagram shows. The next one, the other thing about the yarn is, the yarn takes the appearance and hand of the staple fibers sheath, because on the sheath is containing the staple fibers, and therefore, look wise, or if we try to touch it, it will give the feel of a staple fiber yarn. And the abrasion resistance of the yarn is high due to attached fibers acting as a buffer to the polymer substrate, because the fibers which are there on the surface, they can easily move, and they act as a protecting layer, and because they are flexible, they can move. So, therefore, they can really reduce the abrasive stress. There is variation in the yarn cross section, and if the yarn is passed under a pair of rollers, the yarn cross section may become flat from round, because polymeric material is there, and therefore, if it is passing under a pair of rollers where the pressure is quite high, there could be permanent deformation to the yarn, and the yarn will become more and more flat depending upon how much pressure is acting on the rollers. Applications of this yarns: one is carpet for primary, secondary and for unitary backing, industrial fabrics, filter cloths, paper, trad felts, ducks and twills, upholstery, curtain, car seat and interior covering. These are the possible applications. Bags and packaging materials from jute, other bust and hard fibers, wall covering, tarpaulins, sails, tent fabrics. These are the type of material. Otherwise, other than this, we can have workers cloth, denim, footwear and other heavy cloths. Coated fabrics, obviously once we convert into fabric, then we can coat it, and other backing fabrics for different end uses. Also we can have fabrics which are used at the back, like carpet is always having a backing fabric. So, these are the different applications of the yarn. interlining and other laminates or fabrics where heat sealing and foaming are required. If heat sealing is required, the advantage is polymer is there. So, if we go for heat sealing, if it is required, then we can heat seal it, because the polymer will little bit melt and it will easily seal. So, wherever heat sealing is required, this kind of fabric made from these yarns can be used, or where we have to give a fabric a very fabric has to take a very difficult contour, then also this fabric can be used, because we can go for heat setting of the fabric, and we can easily give a different shape to the fabric. Different 3D shape also can be given to the fabric through the heating process. So, these are some advantages are there, because it is made from polymer material. Major part of it basically is polymer, and this polymer is what is actually they respond to the heat, that is, they will be either they become soft when heat is applied, and therefore, now they can be given different shapes. We will now discuss ABS process, that is aerodynamic brake spinning process. Here on the right hand side, the one sketch of this process is shown. The principle of ABS technology for all practical purposes is similar to open end spinning process. It is based on the utilization of cohesion properties of staple fibers to form a 100% staple spun yarn. Now, here what we do, that a sliver is fed and fibers are separated by an Licarin type opening roller. So, here is the feed side, the sliver is fed here, and there we have opening roller which is opening the fibers or separating the fibers from the sliver. After they are separated, now what happens? The fibers are passed on to the fiber feed roller. See, they are passed on to the fiber feed roller, on which they are held by air suction. So, from Licarin or type of roller, the fibers are going here. This is our fiber feed roller. So, it is. So, there is some speciality about this roller, that is, one is it is a perforated and there are internal suction. So, if I internally sucking the air and the air is entering through the perforations, and if we feed fibers on the surface of this roller, we call it fiber feed roller, then all the fibers will remain stuck on the surface of this fiber feed roller. And then the other interesting thing is there is an adjustable pressure roll, that is this particular roller. The roller is pressed against the fiber feed roller, but this pressure can be adjusted. The other thing that can be adjusted is the rate of air flow and through this fiber feed roller. So, air flow also can be adjusted. And the pressure given by this adjustable pressure roller can also be adjusted. So, two parameters can be adjusted, rate of air flow and the partial pressure nip that is at this point, at the nip point, the pressure that is acting also can be adjusted. These two are adjustable. In order, why they are adjustable, especially this pressure here is adjustable, because we want a braking effect that is necessary for spin, draw, slip, release of the fibers. That is why here we need adjustable pressure. The pressure should not be too high, not should be too low. So, there is a possibility of spinning, drawing, and there is a possibility of slippage. It is not that the pressure is so high that fibers will not be allowed to slip from the nip. Here is the nip. From this nip, fibers should not be allowed to slip. It should be adjustable so that fibers can also slip, but at the same time there is some grip also on the fibers. This is called spin, draw, slip. What happens? Below that we have a twister which is here. So, as the trailing end of the fibers pass through the nip point which is here between the fiber feed roller and the adjustable pressure roller, the nip is existing. So, as the trailing end of the fiber pass through this nip point, fibers are no longer held by the restraining aerodynamic brake forces. See, the aerodynamic force is acting on the upper part of the feed roller, fiber feed roller. So, only from here to there, upper circumference, that means half of the circumference, the fibers are held because of the suction. So, whenever the trailing end of a fiber is passing through this zone, suppose the fiber trailing end is here and then fiber is here, as it is moving down that fiber, the trailing end is at the nip, but really not really gripped because of this aerodynamic force or aerodynamic pressure. Now, whatever torque is applied to this fiber because of this false twister which is here, it will cause the fibers to rotate axially and slip against the leading end of the fibers still restrained above. So, there are some fibers, there are some fibers whose leading end, suppose here is the, let us say this is the nip line. There are some fibers which are here at the nip line. So, and some fibers with trailing ends are here and they are going down now. This is the fiber flow, the nip is here. So, what it is saying that when these fibers which are below the nib line, but the trailing end is held at the nip and they are in contact with the leading end of the fibers which are behind them. Now, if these fibers ends rotate because of the twister which is here, what happens that they will slip against the leading end of the fiber still written there. That means, these fiber trailing end will be able to rotate here also, that is what it is. So, the twister is this point. So, the restraint that is here is not too strong, and therefore, when the forward end of these fibers are under the influence of the twister, the trailing end can rotate. They are not restrained. And therefore, the yarn will be formed and it will not have really it will not act like a false twister, because the trailing end, through the trailing edge some torque will leak. So, the yarn so formed is being drawn off by the take up roller towards the linear take up winder, thus creating a spin draw slip. So, from here the take up rollers are here, I am pulling the yarn out and it is going to the package. So, the twister which is here, normally one would feel that the twister will be acting like a false twister, and if that happens, the final yarn will not have any twist. So, therefore, it will not have any strength. But why it is not happening is because the trailing end of the same fiber, suppose this is the fiber A and B, and the new fiber which is coming, let us say C and D. So, though B and C there is some overlap, but at the nib line, because the pressure is adjustable, we can adjust the pressure. When the A end rotates, the B does not rotate to the same extent. If both of them rotate to some extent, in that case there will be no twist over there, and as it goes down, when this end is rotating, the other end can little bit free to rotate. So, when the lower end is getting twisted in one direction, from the other end, suppose this lower end of these fibers are getting twisted in, let us say, z direction. So, here we expect them to be as twisted, normal circumstances, that will be your first twist. But if the other end of the fiber, that is at the end B, there is some amount of leakage of twist, then the S twist will be little less than Z twist, and when the fibers will pass through this twisting point, the final yarn will show some amount of Z twist in the yarn, because the S twist has become less than Z twist, and hence the yarn will show some twist, and that twisted yarn will be then wound. This is what is known as ABS, aerodynamic brake spinning system, some similarity with the open end spinning system. The final twist in the yarn is equal to the amount of rotational interfiber slippage induced and in opposite in direction to the upstream twist. So, upstream twist is S direction, downstream twist is Z direction. So, final yarn will show some Z twist. Even though the S twisted part will flow to the Z twisted part, but it will not be able to cancel the entire Z, because S part is little less than Z. And why S part is little less, the S twist is little less? Because the end of these fibers are under the adjustable pressure roller, where the pressure is such that the fibers can still rotate, and some S twist will leak continuously through the ends of these fibers. The other technique is felted yarn. So, we initially discussed about the felting process. A schematic is shown here. First point is, a continuous strand of wool fiber is passed through a flexible polyurethane tube. So, this is the yarn feeding directions, and it is going, and here we have this flexible tube. The strand of fibers are subjected to rhythmic compression by a set of rotating rollers. Here are the rotating rollers. This tube actually is agitated. After squeezing, the yarn will pass through the microwave diode, which is here. The most important part is the tube. that is this region. It is passed through this tube, the strand of fibers, and the fibers, the strand is continuously, there is a rhythmic or in a rhythmic compressions. That is a mechanism by which this is done. This is something like this. The strand is following, it is taking a bow shape, it is a wave. So, there is some compression and release, compression release, so that it takes a form like this and it is passing through this tube. Then there are deflecting bars and it is reaching this point, where there is a pressure release holes are there, and that is a very interesting way of actually creating some kind of agitations in the bundle of fibers within a constant space. The constant space is the tube. The fibers have to be agitated, and when it agitated means it has to be agitated when it is little bit of wet, and these agitations, some kind of shaking you can say, will lead to interlocking between the scales of the wool fibers. This process is only meant for wool fibers. Other fibers cannot be really processed and cannot be converted into yarn following this technique. So, this perilock process, which was developed by IWS, International Wool Secretariat, Australia, this was basically meant for wool fibers. There is no twist there. There is no twist. It is all felting. So, felting does not mean, obviously it will not have any twist. It should not have any twist. The original strand may be having some twist to start with, very little twist, but then when the time we felt it, the felting process, the fibers will be basically interlocking, the scales will go inside each other and they will lock themselves. Now, this is passed through the squeezing roller, where the excess liquor is taken out, and the wet material is passed through the microwave dryer, because we have to now dry it. So, the dryer is there, and depending upon speed, time that you require, and the capacity of, see, all microwave dryer, the drying time depends upon what is the count of yarn, how much water is there, how much time it takes to really to evaporate the water. So, the purpose of the dryer is to remove the water. Then the dryer reduces the moisture from 50% to 18% at 25 meters per minute throughput speed for a certain count of yarn. Some data has been given. The point is, it all depends upon the, as I said, count of yarn and how much water is there. After squeezing, how much water is still left over there, and to dry it, we have to find out how much time it gets when it passed through. So, time can be controlled by the speed with which the material is passing through the microwave oven, and then we can also adjust the power of the microwave oven or microwave dryer in order to make sure that in that time period that it gets, it becomes it becomes quite dry, so that not much moisture is left. The yarn is passed through the guide tube and delivered into a large container. This is the guide tube, and this is the container in which the yarn is ultimately flowing down. So, here is the main process which is happening over here, feeding a strand of wool fibers. They must be wet. There is a false twister over here. The purpose of the false twister to give it little bit of round shape, because the tube is round, so it has to pass through the tube, and hence it has to be given little round shape. So, false twister is there. False twister will be able to give it little bit round shape, but it will not have any twist left finally. Then it passes through this tube in wet state, and the tube is agitated, so that there is interlocking between the scales and a stable structure is formed. The rate and the amount of felting depends upon the speed of feeding in and delivery, and on the frequency of the mechanical compressions. That is, here we, as I say, agitate, or we go give the compressive shocks or compressive waves are generated. So, frequency at feed is generated. What is the feed rate, whatever is the delivery rate, all of them will decide the amount of felting that will finally occur. We have to have a reasonable amount of felting, so that the yarn is quite strong and it is processable. The count of yarn could be anywhere between 500 to 6000 ticks, very coarse count yarns, which is can be used in carpets, can be used. The delivery speed can vary in 5 to 35 meters per minute. And with that we close this particular topic, that is, this putty lock process is there, not so really very popular or not really taken up by the industry. Probably some more work needs to be done in order to make it very successful. But the felting process is otherwise common in the case of wool. Many a times we make the woolen blankets are made through the felting process, and felting process can give you very beautiful interlocking between the fibers and quite strong interlocking, and these felts are actually used many a times not only as blankets, but also it can be used in filter fabrics. So, if there is a way to bind the fibers together other than twisting, then felting is a way by which we will be able to really bind the fibers together, and if we exploit that particular binding mechanism to make a yarn, and then these yarns can be used, converted into fabric of a certain thickness, and it can be used for many different purposes. But generally by this process is coarse yarns are made, and as of now at this stands there are not really too many machines which are available. This is not Parlock, but Pedilock machines which are there. And with this we conclude today's discussion on different types of techniques which are still, which people have developed or at different countries at different times, and some of them are relatively successful, some of them are not so successful, some of them have potential to be developed further. With this we close. Thanks.